All right, today we are cracking open the periodic table to take a closer look at a group of elements you probably think you know pretty well. But trust me, they're holding on to some fascinating secrets. Let's get into it.
So let's start with the question. What do iron, copper, and gold all have in common? I mean, think about it. You've got iron, the literal backbone of modern industry. You have copper, which powers basically every piece of electronics we own. And gold, well, it's gold. For centuries, it's been the standard of value. They seem so different, but they all share a secret chemical identity.
You got it. They're all transition metals. But that's not just some random label that scientists slapped on a chart. No, it's a very specific classification with a precise and honestly kind of tricky definition. And that definition explains everything about why these elements are so incredibly special. So let's uncover that secret.
Okay, first things first, we need to know where to find these guys. And for that, we have to look right into the heart of the periodic table.
See that big chunk right in the middle, sandwiched between what we call the S and P blocks? That's our territory. It's known as the D block. And this is where electrons start filling up these really unique energy levels called d orbitals. This block isn't just home to iron and copper, it's got other heavy hitters like titanium, platinum, and silver. I mean, metals that are absolutely essential to our entire way of life.
So you might think, okay, simple enough. If you're in the D block, you're a transition metal, right? Well, not so fast. This is where our mystery really begins, with a very strange little exception to the rule. Take a look at this. On the left, we've got scandium, the very first element in this particular row. It's a transition metal, clear cut. But on the right, you have zinc, the very last element in the exact same row. And get this, it is not considered a transition metal. Wait, what? How can that possibly be?
They're practically neighbors, living in the same chemical block. Logically, you'd think they'd play by the same rules. So what is the crucial piece of information we're missing here? This is the core of our puzzle, and the answer? Well, it's hidden deep inside their electrons.
So, what is this big secret? What's the one rule that separates the true transition metals from the ones that just look the part? Well, it turns out it's actually surprisingly elegant once you see it.
According to the official rulebook from IUPAC, the International Union of Pure and Applied Chemistry, the definition is this: a transition metal must have an incomplete d subshell. And here's the kicker. It has to be incomplete either as a regular neutral atom or in one of its common ions. So just living in the d block isn't enough to get you into the club. You have to prove you have a partially filled d orbital at some point.
And this slide right here is the aha moment. This is where we solve the puzzle. Look at scandium. As a neutral atom, boom, it has one electron in its 3d subshell. That's incomplete. It's in. Now look at zinc. As a neutral atom, its 3d subshell is completely packed with 10 electrons. Okay, fine. But what about when it forms its most common ion, the zinc 2+ ion? It still has a completely full 3d subshell. It never, ever has a partially filled d orbital. And that's it. That's the reason it gets kicked out of the club.
You know, this whole d orbital situation is such a big deal, it actually causes some elements to straight up break the normal rules of chemistry, all in the name of getting a more stable electron arrangement.
Chromium and copper are the perfect rebels to look at here. The textbook says they should fill up their 4s orbital first, but look what they actually do. Chromium literally promotes one of its own 4s electrons up into the 3d orbital just to get this perfectly half-filled, symmetrical configuration. Copper does the same thing to get a completely full one. It turns out that being exactly half full or completely full gives them extra stability, and it just shows you how much influence these d orbitals really have. So we have our definition, an incomplete d orbital. You might be thinking, big deal, who cares? Well, you should, because it turns out this one simple feature is the source of all the amazing, unique properties. They're superpowers, really, that make these metals so incredibly useful.
This quote from our source material really just says it all. That incomplete d orbital isn't just some boring piece of trivia. It is the key that unlocks a whole suite of special characteristics that make these elements different from all the rest.
And what a cascade of consequences it is. We're talking about their ability to have a huge variety of oxidation states, the way they form those brilliantly colored ions you see in a chemistry lab, their totally unique magnetic properties, and their knack for forming complex compounds. All of it, every single one of those things, flows directly from that one simple definition.
If you want a poster child for this, look no further than manganese. It is the ultimate example of variable oxidation states,
Because it has all those d electrons to play with, it can show off every single oxidation state, from +2 all the way up to a whopping +7. This kind of chemical flexibility is the hallmark of the transition metals.
And of course, one of their most stunning properties is their color. I mean, this is their most famous party trick, right? Most other metals from the S and P blocks form kind of boring, colorless compounds. But transition metals, they create this incredible rainbow in a test tube. And it isn't just for show. The color is a direct window into what their electrons are up to.
So here's how it works. The color comes from electrons jumping between slightly different energy levels within those d orbitals. When they jump, they absorb certain colors of light, and our eyes see whatever color is left over. The key is, for an electron to jump, there has to be an empty spot for it to land. That's why you need those partially filled d orbitals. See, iron and copper ions are colored. But our old friend zinc? Its d orbital is completely full, no room for electrons to jump around. The result? It's completely colorless. The rule holds true again.
And you know what else comes from having all those unpaired electrons just hanging out in those d orbitals? That's right, it's also the reason for their classic magnetic behavior. It's the same principle, just showing up in a different, amazing way.
This slide makes the connection crystal clear. The more unpaired electrons an ion has, the stronger its magnetic moment, and the more it's attracted to a magnetic field. This is called paramagnetism. So the manganese ion, with 5 unpaired electrons, is strongly attracted. The nickel ion, with only 2, is still attracted, but not as strongly. And what about zinc? 0 unpaired electrons. So what happens? It's actually weakly repelled by magnetic fields. That's called diamagnetism. It all comes back to those electrons.
Okay, so we've solved the mystery of the definition, and we've seen the incredible superpowers that it creates. Now, let's zoom out for a second and just appreciate how profoundly these elements build and shape the world around us.
Because they can adopt all those different oxidation states, they are incredible catalysts, speeding up reactions like the Haber process that literally makes the fertilizer to feed the planet. Their similar sizes mean they can mix and match easily to form alloys like steel and bronze, the very foundation of our infrastructure. They can even trap tiny atoms like carbon inside their crystal structure to create ultra-hard materials. They're just the ultimate building blocks.
And that really brings us to the final thought. The iron in the hemoglobin that's carrying oxygen in your blood right now. The copper in the wires bringing the electricity to the device you're watching this on. From our very biology to our tallest buildings, these elements are absolutely everywhere. And it all comes down to a quirky little rule about having a few empty seats in their d orbitals. So it makes you wonder, doesn't it? What part of our world isn't shaped by these special metals?